During World War II, caves became more than just hiding places or ammunition stores. In multiple theatres of war, they were turned into living systems, engineered to preserve heat, control airflow, and keep soldiers alive in conditions where tents and surface shelters, just failed. From the limestone hills of Italy to the volcanic rock of the Pacific Islands, soldiers learned quickly that a cave could either drain body heat relentlessly or actually become a stable, life-preserving environment. The difference was not luck. It was a deliberate heat trap method that transformed cold stone chambers into reliable shelters using simple physics and, disciplined setup. Why caves were dangerous before they were useful. Untreated caves are cold, damp, and honestly unforgiving. Stone absorbs body heat rapidly, moisture condenses on walls, and airflow pulls warmth outward like a chimney. Early in the war, troops sheltering in caves often suffered worse cold exposure than those outside. Hypothermia, respiratory illness, and exhaustion followed. Commanders soon realized that caves needed to be modified, not merely occupied. What emerged was a repeatable method to trap heat while avoiding smoke buildup and, oxygen loss. When it came to choosing a place to shelter, soldiers had to be pretty discerning about which chamber they picked. Not every cave space was actually suitable. If you look through World War II field manuals and after-action reports, you'll see that soldiers tended to favour chambers that were set back from the main entrance, but not so deep that all airflow was lost. It was a careful balance, really. The ideal chamber, as it turned out, featured a narrow access corridor that led into a wider room. This design naturally slowed the wind, but still allowed stale air to drift upward and escape. Heat loss was kept to a minimum, without needing to seal off the whole space. And, of course, soldiers always steered clear of any chamber with water seepage or active dripping, since moisture would just cancel out any warmth they managed to build up. Now, let's talk about how they actually created a heat trap with almost nothing at hand. The heart of the whole setup was a layered barrier system. Soldiers would partially seal off the entrance corridor using whatever they had, like ponchos, canvas sheets, sandbags, or even stacked stones, always leaving a controlled gap near the top. This clever arrangement cut down on convective heat loss while still letting some air circulate. It was a simple but effective solution. Inside the chamber, soldiers built low stone walls, or, stacked crates around sleeping areas to block radiant heat loss to the cave floor. Fires were never built in the centre. Instead, they were placed near the entrance or against the side wall to encourage warm air circulation without filling the chamber with smoke. Why fire placement mattered more than fire size? Large fires failed inside caves. They consumed oxygen quickly and drove heat upward and outward. Small, steady fires worked better. Soldiers used minimal fuel to warm surrounding stone rather than the air itself. Once the stone absorbed heat, it released it slowly over hours. This created a stable temperature even after flames died down. In some caves, soldiers heated stones near the entrance during daylight and moved them inward at night, turning the cave itself into a thermal mass. Now, let's talk about how body heat was actually brought into the system. The heat trap, you see, relied on collective warmth. Soldiers would sleep close together, sometimes on raised platforms made from wood, ammunition crates, or even packed earth covered with branches. This setup, well, it reduced contact with the cold stone and concentrated body heat in a defined zone. Blankets and shelter halves were hung behind the sleeping areas to reflect radiant heat inward. This arrangement kept heat from being lost into unused parts of the cave and really focused it right where it mattered most. Now, here's why controlling airflow was absolutely essential to prevent deadly mistakes. One of the most important lessons was to manage airflow without sealing it off completely. Blocking everything led to carbon monoxide build-up and, frankly, suffocation. The tried and true World War II method always kept a high vent or a gap near the ceiling, just to be safe. Warm air rose naturally, carrying smoke and moisture out, while cooler air entered slowly near the ground. This created, a gentle circulation that sustained oxygen levels. Soldiers learned to test airflow with smoke before settling in, adjusting barriers, until smoke drifted upward rather than back into the chamber. In the Italian campaign and on the Eastern Front, caves modified this way stayed significantly warmer than outside temperatures, often remaining above freezing even during snow. Soldiers reported drying clothing overnight and waking without frost on blankets. More importantly, energy expenditure dropped. Less food was required to maintain body heat, and sleep quality improved. In prolonged operations, this translated directly into combat effectiveness. The principles remain valid today. When using caves or rock shelters, select chambers with restricted entrances and natural height differences. Create partial entrance barriers rather than full seals. Elevate sleeping areas using available materials. Use small fires to heat stone, not air, and extinguish flames before sleep whenever possible. Always preserve an upper vent path for airflow. These steps replicate the World War II heat trap without relying on modern equipment. After the war, mobile warfare and mechanized heating reduced the need for static cave shelters. Knowledge tied to specific environments was not passed down widely. Yet the physics never changed. Stone still absorbs heat. Air still moves the same way. The conditions that forced soldiers to master this technique still exist in wilderness and disaster scenarios. Why the World War II cave heat trap remains relevant. This method worked because it respected the environment instead of fighting it. Soldiers did not attempt to overpower cold with fuel. They shaped space, airflow, and material behavior. The result was a shelter that functioned quietly, efficiently, and predictably. If this exploration of wartime survival engineering added depth to your understanding of history and fieldcraft, support in the beginning by subscribing, sharing this episode, and helping ensure that serious practical knowledge is not lost again.